Okay, so this is integration by parts. Which, if I remember right, is section 8.2. Okay, integration by parts is one of these powerful tools used for some rather nasty little problems. Typically, now obviously, if you can do U sub or one of the basic rules, use that rather than this. But integration by parts, typically, it's used for products of algebraic functions which are usually polynomials, rationals, things like this, and a transcendental function. So things like your trig functions, exponentials, and logs. And these are the typical applications of these things. They are used for some other things, but this is majority of what their workload is. Now, again, integration by parts. You want to use only when U sub or polynomial division or basic rules don't work. And we kind of been building after this particular method all semester long. Okay, so here's what well, before I do that, integration by parts is like all integration techniques, they're sort of related to a derivative techniques, and this is based on product rule, which if you think, since we're dealing with a product, if you remember product rule, if I'm taking the derivative of u times v, where u and v are functions of x, so it's going to be equal to v du plus u dv. And this is sort of the basis behind everything we're going to do in here. Or sometimes you'll see this written as v u prime plus u v prime. Okay, and that's the product rule. So we're going to, in order to do this, you need to have the following. So we're going to assume, and if this isn't true, you better not be using this. If this isn't true, you're in the wrong course because this would be Calculus 3. We're going to assume that u and v are functions only of x. And what we're going to end up with is the basic rule for integration by parts is the integral of u dv equals to uv minus the integral of v du. All right, and we got u and v are these functions. Well, this looks really gruesome, but it's not. Important concept on this. Okay, we are taking a bad integral and this is a rabbit dog type of integral, on the left, and turning it into a warm, cuddly, friendly integral on the right. So the whole idea is to take an integral we got here. We don't really necessarily worry about what we're going to end up in there. Some of these can be really nasty looking. What we want to do is find an integral over here which is nice and friendly and easy to do. Okay, so this is our basic ideas of what we're going to do. Here are some neat guidelines. That don't guarantee success. At least not 100% of the time. Okay, so the first thing you want to do, and all our work here is in picking the u and dv. So if we come back and take a look at it, see what we've got here, we've got a u and a dv, and we want to turn this into something over here. So all our work is in picking our u and dv so that we end up with a really nice one on the other side. Here's some guidelines for picking u and v. These are for picking u and dv. Okay, so guideline number 1. Let dv be the most complicated part of the left integrand. You remember the integrand is the inside part. So it's the most complicated part of the left integrand that fits a basic integration rule. If this doesn't work, or if this doesn't work, then try number 2. And dv is usually the one most people try to pick too. So let u be the portion of the left integrand whose derivative is simpler than u. And usually in simpler, we're talking about lower order, but especially where the derivative makes things very simple. Especially if you can get it where it becomes a part of a u sub. So if neither works, then do number 3. Just pick a u and dv and try. So if you hit a dead end Try different. U and dv. And again, most of our problem, most of the work, is in picking U and dv. Choose those wisely and you do well. Choose those badly, you're going to end up with a lot of problems. Okay, so let's work some examples. This is usually the best way to do it. But at least now I've given you some background on what we're doing on this. So here's a nice little example. I have the integral of x e to the 2x dx. Now, don't just pop in and do integration by parts on this. Let's come in and take a look. So let's take a look and let's say, all right, if I do a u sub, then u here will be 2x. du is 2 dx. We're all right, except we've got this x. So u sub will not work on this. Also, notice this is a product of a polynomial which is x dx and a transcendental which is our e to the 2x. And these are usually really good candidates for doing this. Now, the one thing I almost always do is sit back and sort of do some zen on this thing and think, well, you know, this would be really nice for a u sub if I just didn't have that darn pesky x in there. Okay? And this is where integration by parts comes in, because if you choose your u and v wisely, you can get rid of that x. And this is what we're going to do. So the first thing I want to do then is we're going to come in and start picking u and dv. So I'm going to write down my choices for u and dv. So my first choice is going to be that u equals x. dv then will be equal to e to the 2x dx. Okay, now notice on this one, this fits a nice basic u sub integration by parts rule. And du equals dx. And I'm thinking, haha, yeah, that's what I wanted to do. But this is choice one. This is probably the one I want to do, but it's always good to go in and look at your other choices. So we did u equals x. So now let's go in and let's let u equal e to the 2x. And then dv would equal to x dx. All right. Well, this certainly fits a nice basic rewap rule. But the problem is, if I take the derivative of this, I'm going to end up with itself back again, but with the 1/2 out in front of it. So I don't really get rid of the problem that I had to begin with, which is having an x and another one. Also, when I integrate this thing, I'm going to raise my power of x, and what I really want to do is get rid of it. So 2 doesn't seem good. So far, we're going to take a look at 1. Now let's take a look at another one. You're going to think this is dumb, but you're going to have one problem where this will be a good choice. U is 1, dv is basically the whole kit and caboodle we got there, which is x e to the 2x dx. Well, the whole point we're doing all this to begin with, we can't integrate that puppy. Now let me tell you, if you get down and choice 3 is your answer, this is either a u sub or integration by part or a basic integration rule. And it means you didn't check very well. So it's always good to at least take a look at this one. And I've got one other choice here, which is I'm going to use u is. And so what I'm warning you is you're going to have at least one problem which you do not need to do integration by parts on. As a matter of fact, if you do it, you're going to end up with a nasty looking thing coming out of it. So I'm going to let u equal x e to the 2x. And sometimes this is a good choice. dv then is dx. All right, this is pretty good. I know I can integrate it, but again, remember I want to get rid of my x. And the derivative of this is a product rule. So that basically violates guideline number 2 we're dealing with, which is that we want to make sure that our du is simpler than our original u. So basically, at least at first glance, choice number 1 appears to be the one we want to go with. So let's come in then and let's deal with number 1. So what we got here then is that my u is x, my dv was e to the 2x dx. So if you remember integration by parts, the integral of u dv, which is what we started out with, is going to be uv minus the integral of v du. So we need to get v and we need to get du. So du is nice, it's dx. V is the integral of e to the 2x dx, which is 1/2 e to the 2x. And now we can come back in and start to integrate this thing. So the integral of x e to the 2x dx equals, so it's u times v, so I'm going to have 1/2 x e to the 2x, which looks nasty, but remember we're not worried about that one, minus, because this is what we're interested in, is getting a nice simple integral. So it's v, so I'm going to have a 1/2, bringing that out, e to the 2x, du is dx. Well, hey, howdy. We've already done that. And here it is, again, well, with a 1/2 out in front of it. Whoop-dee-doo. So now we've got 1/2 x e to the 2x minus, and I've got to bring my other 1/2 out, so it's going to give me a 1/4 e to the 2x plus c. And here is our integral of this guy. Okay, it seems like a whole lot of work, but again, remember we've got this thing right here, and I know I've got a u sub if I can just get rid of this, and taking the derivative of a polynomial brings down its power, which is what I was after. Okay, so that's that one. Let's take a look at another one. So this one I'm dealing with the integral of natural log of x squared dx. So if we do a u sub on this, my u would be natural log of x And du is going to be, actually will be dx over x, and we don't have that. Okay. We've got the dx, but we don't have the over x. So I can't do u sub on this. And you think, well, we really don't have a polynomial, but we do. It's just 1. So the first thing I'm going to do then is I'm going to come back in, and basically with this one we're only limited to 2 options. So my first option is I'm going to let u equal to natural log of x squared, and then dv is dx. Okay. Well, this is a little problematic, but we've definitely made things easier here. Except, but what we need to worry then is our du, okay? And that's a product rule. So let's take a look at our other option, which is that u is 1, and then dv is our ln of x squared dx. Well, that didn't help us either, because that's kind of what we started with. So if you look at it, we're basically stuck with this puppy right here. We have no other choices. Okay. Now, while we can integrate dv, it's going to be nasty handling this guy. Also, it's not really going to give me my u sub. So what I need to do then, this one's out. I need to find du, and this is chain rule. So it's going to be 2 ln of x times the derivative of ln of x, which is dx over x. Okay? And v then is going to be the integral of dx, which is x. So now we come in and we plug everything in. So I'm going to have uv, so I'm going to have x times the natural log of x squared minus the integral of v, which is x, times du, I'm going to bring my 2 out, ln of x times dx over x. These guys go away. So I'm going to end up with x times the natural log of x squared minus 2 times the integral of the natural log of x dx. Or I have x times the natural log of x squared minus 2 times x ln of x minus x plus c. And there's my integral. Okay, let's take a look at a really nasty looking one. And on this one, we're going to use integration by parts multiple times. Okay, so our function looks like this, and this is like a rabbit pit bull. X to the cubed times sine of x dx. So what we're going to do is repeatedly use integration by parts on this thing to beat it down where you've got a nice, friendly, cuddly little Labrador Retriever puppy that we can handle. Okay, again, we go back in and let's check out our options. So one option then, obvious one is u is x cubed. Okay, and dv is sine of x dx. Now at this point I take a look at this and say, well, you know, if all I had was just this thing, in other words, if I could make this guy go away, then I'd have a really nice little integral. Okay, now remember we're taking the derivative, but this is x cubed, so this gives me some idea that I'm going to have to do this thing 3 times to bring my x cubed down to a dx. Well, let's take a look at our other options. But there's the first option, and this looks pretty good because this definitely meets our guidelines. And du, we do bring down the order of our polynomial, which is what we want to do. So number 2, but let's take a look at our other options. So we're going to let u equal sine of x. bv then would be x cubed dx. Okay, so right now this is my preferred. But let's take a look at this guy. Well, the derivative of sine is pretty easy. That's cosine. But when I integrate this thing, I'm going to actually raise the power of x. And the problem is, I want to make it go away. So if I integrate this thing, now obviously this is a nice friendly little rewalk. The problem is when I put everything together, I'm only making my problem worse in that instead of reducing the order of x, I'm increasing it. So let's try the dumb solution, which is you overlook the obvious. U is 1, dv is x to the cubed, sine of x dx. All right, so if I do that one, no. There's no way we can do any u sub. There's no integration technique I know of to handle that. Although, boy, that's really nice to take a derivative of. It's 0. So number 4, my last option that I want to take a look at then is I'm going to let u equal x to the cubed sine of x, and dv then is going to be my dx. This is always a good one to look at. The problem is, and that works well, except that again, when I integrate that, I'm going to raise the power of x. This is a product rule. That thing's not going to look good at all. It's sure not going to make it simple. Remember, we want the most complicated thing that fits a basic integration rule, and we want to try to reduce the power of u. So, and make it simpler. So basically, let's go with choice number 1. That seems to be the best one. All right, so let's do this guy. So I know my u is x cubed, dv is sine of x dx, du is 3x squared dx, v is the integral of sine of x dx, which equals to negative cosine of x. And then we plug everything in. So I've got u and v, so I'm going to have negative x cubed cosine of x minus the integral of v, it's a negative, so I'm going to do that, cosine of x, and then I've got a 3 and an x squared, cosine of x dx. Okay, we still can't do this one. So I come back in and think, okay, so do I want to go back in and try one of my other options? Well, so I go back in and look again. I still don't like this one because my problem, as always, is the fact that I have a power of x here, and this one is still going to raise it. I went in and I've already figured out that no, I didn't bypass the obvious. And this one I really don't have to deal with a product rule in there if I can help it. But I do notice that, okay, I started out with an x cubed. Now I'm down to an x squared, which is good. So what do I do then? I do it again. So now we're just going to deal with this part only of this thing. Only this. This guy is just going to get copied down. And whatever we do, we're going to multiply by 3. So we're going to do the same thing we did before. Let's take a look at our options. But in this case, I'm going to go ahead and stick with option number 1 because it's doing what I want to. It's bringing down the power of my x. So my u is going to be x squared. dv is going to be cosine of x dx. So du now is 2x dx. See, I've reduced it again. I know I'm going to have to do it again because I've got too many. And v is going to be the integral of cosine of x dx, which is sine of x. Okay, so there we are. We're about ready to go here. So now we plug in. Now this guy I just copied down. So I've got negative x cubed cosine of x plus 3 times, now I do my integration by parts, so uv is going to have x squared sine of x minus the integral of v du, so I've got a 2 out front of here, and I've got an x sine of x dx. And I'm going to go ahead and distribute through here. So I've got a negative x cubed cosine of x plus 3x squared sine of x minus 6 times the integral of x sine of x dx. Okay, again, I want to come back in and kill out my integral. But see, I started with x cubed and I'm down to an x. So what I know then is I have to deal with one more time, but I only have to deal with just this. Again, these two terms are just going to get copied down. So again, I'm going to deal here with u, but I'm just, okay? And dv is going to be sine of x dx. You should have recognized that we've already integrated sine of x dx. There it is right there. So v is negative cosine of x du equals dx. And this is what I'd hoped to get to begin with. I've got no x, I just got a d. Hallelujah. Okay, so now we come back in. I copied out all that mess I had before. Now you notice a lot of this is just copied stuff you got before. The equations look pretty impressive. And they're really good to show the idiots that are sitting in the history of math and amaze them with your algebra skills when all you're doing is just copying the same stupid thing down over and over again. And this times. So I've got u times v, so it's going to be a minus x cosine of x minus the integral of v, which is a negative cosine of x, that makes that a plus, du. Well, Guys, we've already done this one too. We've already integrated cosine of x dx. So now what I'm going to do is go ahead and distribute everything. Well, before I do that, so we've got negative x cubed cosine of x plus 3x squared sine of x minus 6, should be a plus, negative and a negative, plus 6x cosine of x. And I'm going to integrate. So the integral of cosine is sine, and I've got distributed in that negative, so it's going to be minus sine of x, and it's going to be 6 times that, plus c. And there it is. Seems like a lot of work, and a lot of it is, but if you take a look at this, really most of this was picking the right things at the front and then sticking with them. Okay, so before I go, I know this is getting long, but let's sort of come back in. So notice on the problem, notice with an x cubed, I needed 3 integration by parts to get to an integral I could do. And this is pretty typical. And again, sometime, brother, if you take a look where they interview some of these physicists and stuff, they've got all these horrible looking equations. Come up and take a look, and I bet a lot of what you're seeing up there is either going to be chain rule or just a bunch of little integration by parts done over and over and over again. Also, notice so I wasted, or did I, a lot of paper writing down my options. For u and dv. Also, I wasted, or did I, a lot of time looking at the options. And what I gained.